Hello, welcome to Basics of Noise and its Measurement. This is the second day of the last week of this course. Yesterday we were discussing short-term discrete Fourier transforms, and we had discussed as to how we can splice up a long time series signal and successively FFT to get time-related information, time-related frequency spectrum of the entire signal. And this approach becomes particularly handy and useful when we have non-stationary signals, that is signals for which the frequency spectrum keeps on changing as time marches forward. So now what we will do is today is we will actually continue that discussion on short-term discrete Fourier transform. We'll actually look at some examples, and then we will conclude today's session by discussing this another very useful tool known as a spectrogram. So that's what we are going to talk about today, short-term Fourier transforms and spectrograms. Now I wanted you to look at this signal, and this is y equals 3 times sine of 2 pi times t over 2 times t. So that is basically pi times t square over 2. So here my frequency, so the reason I have put t over 2 separately and I have not merged it with the other t is that my frequency, which is this thing t over 2, it is actually increasing as time is marching forward. So at t is equal to 0, the frequency is 0 hertz. At t is equal to 1, frequency is half hertz. At t is equal to 2, frequency is 1 hertz, and so on and so forth. And when I plot this signal on x, on the time axis, that's the plot, time in seconds, and I have plotted it for 6 seconds. Vertical axis is amplitude, and what you see is that as time marches forward, the frequency of the signal keeps on going up. You may hear something similar. For instance, if there is a car and which is racing and it's accelerating, you may hear some noise kind of similar to this kind of a signal. Okay. So now if I take the FFT of this, if I take the FFT in maybe first second, my frequency will come out to be, say, the most dominant frequency will come out to be maybe something close to half a hertz. But as I increase, move my window rightwards, the frequencies which are dominant as my window moves rightwards, the dominant frequencies, they keep on going up. Okay. So this is one example, and in this example, the frequencies themselves are shifting with time, and this is an example of non-stationary signal. Now this is another non-stationary signal. So in this case, the frequencies were shifting with time, they were actually in this case increasing with time. This is another example. So what you have here is another signal on the y-axis time, x-axis time, y-axis amplitude, and you have y equals a1, and a1 is the amplitude, and that is a function of time. So a1t times sine 2 pi f1t plus a2t sine 2 pi f2t plus a3t sine 2 pi f3t. Now what are the values of f1, f2, f3? f1 is 1 hertz, f2 is 5 hertz, f3 is 50 hertz. So the frequencies themselves are same, but the amplitudes are time dependent. So a1 is linearly changing with time, a2 is having a square root relationship, and a3, interestingly, we have chosen that it is a sinusoidal function of time. So the amplitude of this signal, last component of the signal, which is 2 pi times 50 hertz, it is basically 2 pi times 1 hertz t. Okay. So the amplitude of this signal, initially it is 0, then it goes up, then it comes down, then it goes up, then it comes down, and so on and so forth. So this is another thing. So now what we will do is we will use our windowing technique and use we did this short term DFT of the second signal, and we will show you some of the plots. Okay. So what you are seeing here are 12 graphs, 1, 2, 3, 4, 5, 6, and then start again 7, 8, 9, 10, 11, 12. These are 12 different graphs. As you look at these graphs, please be aware that the x-axis is same, 0 to 100 or 600 hertz, but the y-axis, the range is different. So the range is minimum here, it's 0 to 1, here it becomes 0 to 2, but here it becomes 0 to 4, here 0 to 5, and then finally it becomes 0 to 10. So as you are making judgments about these graphs, please be aware that the vertical axis are changing. The first graph corresponds to window which is half a second long, and this is the first half second of data of that entire 6-second long signal, and we took its FFT and the results have been plotted here. And what you see here is that you see a peak at 50 hertz, which was indeed the case because there is a 50 hertz frequency, okay. And then you also see a small another peak at maybe 2 hertz. So if had we plotted this on the log scale, this would have been clear. So this is at 2 hertz because there is another frequency at 5 hertz. So this is 5 hertz. But then you will see, if you zoom in on this, you see some absurd data at 1 hertz, below 1 hertz. And the reason for that absurdity is that our time, duration of time is only half a second. And to capture accurately the FFT of a 1 hertz signal, which is this first component and this signal, I should have signal which is at least 1 second long. Even at 1 second, it's not always guaranteed, but it should be at least 1 second long. So you see some absurd results, but you get okay results for 5 hertz and 50 hertz frequencies. And then you see that the value of A1, A2 and A3, it keeps on increasing with time. I mean, this also increases, and it only actually becomes small after one cycle is over, when after 1 second. So that is what you actually see, that it has increased, everything is increasing, and then this increases, everything is increasing, and all these amplitudes, the first 2 amplitudes, they go on increasing. Same thing here, the first 2 amplitudes keep on increasing, and it's just that, and this amplitude actually, if you calibrate yourselves, because the vertical axis is scale is different, this actually goes up and down and go up and down and up and down, because here the scale is now 0 to 10. So on the time scale, it is this analysis, this short term DFT is giving us decent results, but on the frequency scale, at least for 1 hertz component, which is this particular component, we are not getting good data. So this is there. So then we said, okay, so this is, and again in this case what we are doing is we are taking FFT of the first half second, then we move rightwards by another half seconds, and then take the second half second, then third half second, fourth half second, and so on and so forth. So that's how we are getting 12 different graphs. While generating these graphs, we were not having any overlapping of the windows. So this is there. Then these are 6 graphs, and these correspond to windows which are 1 second long. And once again, here also the windows were not overlapping. So we took first second, second, third second. So that's why we have 6 graphs. And what you see is something very interesting here. So if you zoom in, you get much better resolution, somewhat better resolution of 1 hertz and 2 hertz. But you see something very interesting, that at 50 hertz you are seeing 2 frequencies. Okay, you are seeing actually 2 frequencies at 50 hertz, and you wonder why is this happening, and the reason for that is this. So actually I'll explain this on the. So what was our original signal? Our original signal was y equals A1 sine 2 pi f1t plus A2 sine 2 pi f2t plus A3 sine 2 pi F3t. And we had defined that A1, A2, A3, they were not constants, but they were functions of time. So A1 was basically t, A2 was, we had defined it as root of t, and A3 was sine of 2 pi F1t. Okay? And F1 was 1 hertz, F2 was 5 hertz, and F3 was 50 hertz. Okay. Now what is happening is that at around 50 hertz in the graph, when you see it, you are seeing two frequencies. You are not seeing one frequency. We will see that again. And why is this happening? So we will look at this component in detail. So your A3 is basically sine 2 pi F1t times sine 2 pi F2t, right? Which is, and what is F1? Or sine 2 pi t times sine 2 pi times 50 times t. This is what is there. So this is sine A times sine B. And if you go back to your classes of trigonometry, you will see that these multiples of two sine of A and sine of B, it can be resolved into the cosine of A minus B and A plus B divided by 2, right? So this is nothing but, this gives us one component cosine of 2 pi 50 minus 1 divided by 2 t, and the other component you get is cosine of 2 pi times 50 plus 1 times t divided by 2, which is cosine of 2 pi times 49.5 times t, right? And this is cosine of 2 pi times 50.5 times t. Okay. Now, this phenomena, so the actual signal, when you do the FFT, when it does the FFT, it is detecting these two frequencies, 49.5 and 50.5 hertz. Okay. It's detecting these, and it's doing a good job. It's doing this is the right thing, right? It is detecting these two frequencies, and it is detecting it. Why? So in the first graph, when the duration was extremely small, it was not able to detect these two frequencies. It was not able to resolve these two frequencies because our delta F resolution was what? Our total duration was half hertz. So our resolution was 1.0 1 over 0.5, and that is equal to 2 hertz. So I could not separate those two frequencies. Okay, it could not separate those two frequencies accurately. When I increased my duration of time to 1 second, my resolution went down to 1 hertz. Okay, it went down to 1 hertz, and so it is able to resolve. So that is why you are seeing these two peaks. These two peaks should have been there, because when you multiply two frequencies, you can also express them as sum of two different frequencies, right? And so these two frequencies are actually real, but you do not see when your duration of time is very less, because your resolution is not that much. So that is what we mean, that if my duration becomes very less, one problem I am having is at 1 hertz. One problem I am having is at 1 hertz, because when time is very less. Other problem I am having is also at 50 hertz, because there also there are two frequencies present, but it is not detecting them, because again the resolution is not there. So again, when I reduce my time, I lose frequency resolution. When I increase my time, I lose time related information. So this is what is happening. Now let's look at t is equal to 2 seconds. So this is t is equal to 0 to 2, t is equal to 0 to 3, 2 to 4, and t is equal to 0 to 4 to 6 seconds. And what you see here is that the time information now, so again, I mean, you have two frequencies here. So frequency information is there. All the frequencies have been correctly identified, right? But the amplitudes, you cannot say at what time these amplitudes correspond to, because this is for a 2 second long interval, right? It is for a 2 second long interval. So is this time, the first graph is for 0 to 2 second. Is this amplitude corresponding to t is equal to 0, or is this amplitude corresponding to t is equal to 1, or is this amplitude corresponding to t is equal to 2? You do not know. The only thing you know is that for that whole duration the amplitude is 2 seconds. If you use this to reconstruct, do the inverse FFT in reconstruct, you will not get good answers. Okay, so this is what I wanted to show in context of this short term digital Fourier transforms. This is very important to understand that windowing is important and it helps us, but you are seeing it here very clearly that if I increase the time, I get better frequency resolution, but I lose time information, and if I reduce the time, I lose frequency information, but I get better time information. So I have to balance and have a compromise between these two conflicting stands. So this is the signal we were discussing. Okay. So the next topic we will cover is spectrograms. So these spectrograms come by different names. Okay, they are also known as waterfall diagrams or waterfalls. They are also known as voice prints, especially if you are synthesizing and analyzing voice samples. They are also known as voice grams. Okay, and the concept here is pretty much identical to what we had discussed in context of short term discrete Fourier transforms, but the nature of representation of these graphs is, or this data is different. So in short term what we had done was we had generated a large number of graphs, you know, for different durations. So duration 1, duration 2, duration 3, and so on and so forth. So you have to make 12 different graphs, and then you have to look at those graphs carefully and interpret and see what sense you make out of them. Spectrograms, you you compress all that information into one single picture. So in a spectrogram, what do you have? You have on this x-axis you have frequency, or you can also have time. So the one which we are going to see will be frequency, time. On the y-axis you plot frequency. Okay, and what do you plot here? Here at each point you plot different points so you plot all sorts of points, but each point represents amplitude of frequency component corresponding to time t. Okay, so each point and the color of each point. So I should have written color of each point. Each point represents. So if your scale is such that red is extremely large and blue is extremely small, then red will represent that the amplitude is maximum and blue will represent amplitude is minimum. So this is like a three-dimensional plot in two-dimensional space. So this is what this is, okay? And this is also known as, there is some fancy terminology, spectrotemporal representation of sound. So what is a spectro? You are plotting, giving the frequency information also, and then temporal means you are also giving time information through this spectrogram. You can generate this spectrogram. Your input will be, what is your input going to be? Input is going to be a string of numbers, right? Or what are these numbers? They are basically values of pressures which you have measured, right? So this is basically a function of time, right? So these are all the values of pressures at different values of times, different t. And then using this windowing method, you generate the spectrogram. So what I am going to show you are a bunch of spectrograms for two different functions. And while you are generating this spectrogram, there are 3 or 4 important parameters you should think about. So the first parameter is x, or so that represents your raw time data, okay? Then the next important parameter is, let's call it w. So this represents size of window, okay? And typically, so how long your window has to be? Is it going to be half a second long, 1 second long, and so on and so forth? But you don't typically represent the size of the window in time, but rather in terms of number of points. So if your sampling frequency is, let's say, 1000 hertz, then you say size of window equals 500, that will mean that the duration over which you are going to do this thing will be half a second, right? So this corresponds to delta t is equal to number of points divided by fs. So from this you can calculate number of points if you are more interested in delta t, okay? And then the third one is O. This is size of overlap. Size of overlap. Okay. So what this, and this is again in terms of number of points. So you can have window 1, then your second window can be like this. So whatever are the number of points in this range, that is your overlap size. This is your O. Then your third window could be this. Your fourth window could be this. And so on and so forth. So this is, so overlap, size of window, all these are specified, at least in context of MATLAB, in terms of number of points. And then the spectrogram, you can plot it in all sorts of ways. So what we will do is, we will actually look at some of the results. So this is the function, we have discussed, and what we are going to do is, we are going to look at its spectrogram for different cases. In first case, we will have half a second size of the window, and there will be no overlap. Then we will look at, so this is the spectrogram, okay, and you are seeing two pictures, and I'll explain you, but both of them are for half a second. See, it says window length is 512, sampling frequency is 1024, which means the window size is half a second long, okay, and it says overlap samples is 0. So both of them are overlap samples is 0. The only difference here is that in this case my y-axis is frequency in a linear scale, and here I am plotting on a dB. Here I am plotting on a dB. That's the only thing, okay. So here I am actually plotting it on a, don't worry about dB, it's basically on a log scale, okay, and x-axis is time. So what do you see? So here only at low end, okay, I have only 3 frequencies total. One is T is equal to, F is equal to 1 Hertz, 5 Hertz and 50 Hertz. What do you see here? This entire band is yellow. So ignore this one because I don't see frequencies at low frequencies clearly. But if you look at this log scale plot, then this is 0, no, this is 1 Hertz and this is 10 Hertz. This tells me that all the frequencies are present between 0 and 10, okay, which is wrong. And it is wrong because my duration of time was very small, so I am losing frequency related information. I get a good frequency related information at 50 Hertz. This is 50 Hertz because the time period for 50 Hertz is very small compared to the duration of my window. So I get decent information here. So I am losing time information here, okay, and here in overlap was not present. Now and this is the same graph but overlap was present. So you see some probably more gradual transition. So I am not going to talk too much about that. But here this is the same plot but overlap was more. There was overlap, so it is moving gradually rightwards. Then the other one is sampling frequency was 1000, window length was 1 second or 1024 points. And then again I will look at this, and when this thing becomes 1 second, you see first thing is that you see 2 lines here, right? At 50 Hertz you see 2 lines. Yellow means its intensity is more. This is more, this is less. This yellow, this color is also on a dB scale. So this is 0 dB, this is minus 120 dB. So 120 dB is extremely small. So this yellow means more, so which means that there are 2 frequencies present, which is actually the case, which we had seen earlier. Then the other thing is that around 5 Hertz you see 1 band, then you have a green, right, which means there is no frequency at this end, and then you have some more information here. So you see some 2 frequencies here, 3rd frequency here, 4th frequency here, but here again it is still pretty wide. Actually this log scale should have been, maybe we should have made it better. We should have started from 10 to the power of minus 1. Then I could have clearly see 1 Hertz. So then we look at the 3rd graph, and here the window length is 2048 points. So since our sampling frequency was 1024, this is 2 seconds long, and here what you see is there are 2 frequencies here very close to each other. Then there is a 3rd frequency at around 500 Hertz, and then this is 10 to the power of 0, which means 1 Hertz. So you see a dark color here, between this point, and then here it becomes lighter progressively. So there is some energy at around 1 Hertz. So you get more information for 1 Hertz when you increase the sampling size, which is what we expected. But then what you see is that the time related information is getting increasingly blurred, because I have this hole is 1 window, 0 to 2 seconds. So nothing is changing in 0 to 2 seconds, okay. But in reality the amplitude has grown for the first frequency from 0 to 2, because its amplitude was t, but that is not shown here. But if you go back, in the first case you see that amplitude is growing. You know, this is orangish, which is minus 20 dB, and this is yellowish, which is 0 dB. So amplitude is growing. So time related information is more present in this graph when your sampling frequency is, when your window size is small. But time related information you are losing. So this entire thing is homogeneous. Then you have another homogeneous color, then you have another homogeneous color. So you lose time information, but you get frequency information more. So this is again to show these plots. And then the second set of graphs which I am going to show you is for this function, y equals 3 sine 2 pi t over 2. So here the amplitude is constant. The only thing which is changing is frequency as a function of time. Initially frequency is small and then frequency keeps on ramping up. And what we have done is again generated this signal for 6 seconds at a sampling rate of 1024. So this is my window length when my window is half a second long or 512 points. So again, I mean, if you look at this graph, not necessarily this graph, but on the decibel scale graph, when we have the frequencies on the log scale, you see that you have a lot of time related information. But especially for the frequency you don't see a whole lot of stuff, okay. And then as this window length increases, then this time related information starts getting blurred and you get more and more information about frequencies because the resolution and the frequency, see here on the y axis the resolution here is less, but here you get more finer bands, right. So you get finer bands, so you get more information on resolution. Here the bands are even finer, so you get more information on frequency. So these are the two things I wanted to share, and I hope that these concepts and tools for spectrogram and short term DFT, they will be useful for your applications. And what we will do tomorrow, so this concludes our lecture for today, and what we will do tomorrow will be something related to reverberation time and concepts related to reverberation. So thanks a lot for patiently listening to this a little long lecture, and we will meet tomorrow, and have a great day. Bye.